Hello, everyone. Welcome back. So if you don't mind taking your seats, we are a little bit behind, even with modifications of the time. So that's my honor to introduce Dr. Hayashibe. So he's going to talk about human-like motor control in redundancy through deep reinforcement learning. Please.
Yeah, thank you for introduction. And actually, my talk is not really related to surgical applications, but I think we want to reproduce human motion for surgical tasks. So in this sense, I think it's very much highly related issues. So we all know that there's a robot joint. So let me, oops, yeah, yes. Okay, yeah, fine. Yeah, we have a redundant joint. So thanks to this redundancy, we can do the complex task. And this is an example of silhouettes of human body and for like many motor tasks and like Olympic game, remarkable issue is human same body, but we can manipulate our body for doing different tasks. And still, maybe one robot can do one or two tasks, or it's possible, but it's impossible for having one robot to do this type of multiple different motor control. Okay. Yeah, and if we look at our daily life, actually we use this redundancy very nice way. And yeah, of course, you often go to supermarket and maybe you notice that you hold basket from the side at the beginning. And even we don't think and we don't have some such consciousness to change joint coordination, but you may notice that after buying many items in basket, and in this case, it's different the style of arm postures for different ways. And if you imagine why we do this change is it's not to waste energy. So our main task is to do that carrying object task, but in the behind we have second objective is not to waste energy. And yeah, already I assume you know the redundancy, and human body have joint redundancy and also muscle redundancy. And we, in the sense of optimization sense, because we use learning function to optimize. And one is the performance, motor task, but second is always energy minimization. And when we look at joint usage, maybe you may heard about synergies, motor synergy. It means in the redundancy, we employ very similar patterns over different persons. So there's specific spatial temporal pattern, and we call this as synergies. So already, this is a mathematical method to do the dimension reduction and test how many, real dimensionality is there for motor control. And already this hypothesis is verified in neuroscience context, and already it can explain well the real human behaviors. And this is the example for a baby to reach an object. So this is not learning, this is learning by real human agent. And in this case, initially that 19 weeks later, he cannot move end point straight. But after 42 weeks, it starts to find optimal pathway. And this is endpoint trajectory. And when we look at the joint coordination, initially the joint elbow, shoulder move independently, but somehow he finds the synergetic way of using joints. And finally, that it's very aligned between the shoulder and elbow. So he finds it's very efficient to move elbow and joint together. So this is one reason why we employ synergy and to find optimal motions. And the synergy study, in fact, many are like human observation and animal observation. So like biological system and take the observations and analyze and check the dimensionality, and this is so-called synergy studies. But I want to move from just observation to creation of motor synergy. And in this way, we can find what is the computational principle behind for human motor control. So in this talk, I just show some example, and yeah, of course, not for everything, but we want to try to reproduce how synergy reproduce or emerge through the deep reinforcement learning. Yeah, and this is a motion of baby, and already we can find multiple joint redundancy there, but we find specific spatial temporal patterns, so it means already emerge of motor synergies. But point in this talk is how human animal find motor synergy computational sense. So this is the target of this study. So if we can reproduce, we can understand better and what is the computational principle behind. Yeah, and the previous talk, it was very nice talk about soft robotics, and it's true that the soft robotics is very difficult to predict initially what is output for corresponding input. But somehow by inputting many patterns of input and output, find possible to create a neural network like previous talk. And actually human also create such process. That's why if we, for example, if we create pressure like air from the mouth, I think initially we don't know how to change the pressure, but after try and errors, we find the input-output relationship. And having kind of neural network model, using this model, we can inverse the problem and we can directly create necessary input. But this is relatively simple in the sense criteria is only minimizing estimate errors. But the human, coming back to the human motor control, in fact, not single criteria. And in redundancy, we can optimize not only one objective, and we can optimize task performance and also energy minimization. And in this human motor control area, this is very famous work by Professor Todorov, and he showed using optimal control theory, we can reproduce human-like behavior. But in fact, somehow a little bit problem setting is different because of course solution is optimized, but he starts with the assumption already that the dynamics equation is known. But for example, baby, we don't know the environment and our body change. And in this case, we need to recreate new dynamic equation and we need to optimize again. So it's easy to optimize after we have the mathematical equation. But there's a problem of using model-based optimization directly in human motor control. So first, we don't know dynamic model directly, and sometimes animal-human change our mass information. And in this case, really we need to update it, and we really need learning function. And often optimization approach needs separate process between optimization and then control. But human, as you know, we optimize and control at the same time. So we need a new framework which can manage non-separated optimization and control framework. And also dynamic condition is not static, and we hold new tools or something, and our mass change and inertia change, and we need to obtain new dynamic equation, but actually not that easy task. So we decided to go for deep reinforcement learning. So reason is we need to optimize motor performance, but also energy effect. And in highly redundant system, to optimize a multiple objective is challenging. So we decide to use reinforcement learning and try and error, and also neural network is nice to create the neural network model to represent input-output relationship. So we use these two together. So maybe you already know basic of reinforcement learning, and this is possible to find optimal solution by try and error basically. And the main key point is, as you know, that time delay feedback is usable. So even after long actions, if we find the foods, that we can still take into account how we find like some delayed reward is also possible. And this is typical framework for reinforcement learning. And yeah, and of course, objective is to find action, and depending on the state, and we try to create the policy by neural network, and after that learning, after receiving the knowing the current state, we can create necessary action directly after the learning. And the same for even if we have motor performance agents, it's the same thing. And initially he cannot move efficiently, but by try and error, he finds to improve the motor performance, but also the energy effective motions. And this field is already like 10 years, and you may heard about OpenAI. You may seen this type of motions. And also, you may know that this is a DeepMind work, and this is very impressive to 2017. And rarely he can find or systematically find the task management. But problem is that not really human-like. So I think what is missing for improving this performance. So point is not synergetic. There's no good elbow shoulder coordination. But it's really he optimized task only. So but he still don't optimize energy aspect. So I decided to optimize also energy efficiency. And we checked different reward setting and find in which condition we can create effectively the synergy. Time is limited, so I try to follow the schedule. So finally, point is we published the journal paper, RAL paper 2020, and point is we find how to efficiently create energy and synergy. And the point is it was highly correlated to the performance per energy. So yeah, if we know the mechanical dynamics, it's logical to think if we use shoulder elbow together, we can minimize energy to find efficient motion. So this is we could confirm that to make synergy emergence efficiently, that there's an energy behind. So initially that we don't know that which joint is located which limb, but finally he finds same phase for same limb. inside the same limb, but for front and back, he finds the antiphase pattern. So, but we find that similar spatial temporal pattern over the joint, so we can actually compress the input space. Actually, not totally independent, and there are some common patterns over the joint. So the real input space is very compact. So we checked how much compact. This is the number of PCA, and increase proceeding the learning, we find that we can represent this performance with reduced PCA components. So it means that synergy is emerged. So of course, we change the mechanical condition. This is a normal agent. And we change the more heavy trunk. And of course, spatial temporal pattern gets slow and different pattern, but the process, how we emerge the synergy is the same. And the interesting point is there's a relatively old reinforcement algorithm and a new algorithm, and interesting to find SAC is well known and very performing deep reinforcement learning algorithm, and this nice algorithm use synergy more for all different conditions. Yeah, time is limited. So we tried also for human reaching one. That was initially the cheetah, but now human motion creation. And we never use human motion data here. And purely by computation, we could make nicely synergetic joint coordination. So we can reproduce human-like motion without using any human data. So I think that its reason is that the energy efficiency behind always for human motor control. Okay, time is limited, so let me go a little faster. And also we have the process that initially feedback control or control is dominant, but after that feed forward is compensate and take over the feedback. This is same to human motor learning. And after that, actually, we can control also the modes of gait. Maybe you may heard about trot or gallop. And in reinforcement learning, we have still enough redundancy, so we can specify, okay, please try trot mode or gallop mode, and we can verify which mode is efficient. So it's kind of synergy difference for gait. Yeah, and we change the speed of the gate, and we check which synergy mode is efficient type for this speeds, for different speeds. And still not fully study, and we are still doing the work, but it was interesting to confirm for higher speed, gallop was more efficient than trot, and for lower speed, trot was more efficient than gallop. So it's same to animal horse motions. And also, this is the last result I share, and this is still simple human control, and it's maybe you can try this. Just he is moving head and for different speed, and it's known in biomechanics that in phase motion for slow, when we move head slowly, ankle and hip move together in the same phase. And for faster speed, it gets anti-phase. This is, if you try, you find you move like this. So this is kind of optimization, and he switched the mode of using joints. And we try to reproduce, again, same method, deep reinforcement learning. And point is, of course, task is head motion, but also we also optimize energy efficiency. So in this case, similar to human motor control, it's in phase for slow speed frequency, but at certain point, he switched the anti-phase. and this is still simple, but we find this type of energy and synergy concept can help to recreate human-like behavior. And of course, still simple motor tasks. So by keeping this concept, I believe that we want to expand this, result for more different motor task, and we want to reproduce human-like motor control for more variety of motor tasks. Yeah, so it's time. So I share this result, and this is I'm from Tohoku University, so 1 hour and a half from Tokyo. So if you want to visit Sendai, please tell me. And yeah, this is the end of my presentation.
Let's thank Dr. Hayashibe for his interesting talk. We have time for one quick question, and we need to switch to the other speaker, please. Jane, please. Any questions? If there is, yeah, go ahead. Jane, you can go for some.
Hi, I maybe wanted to know what you think of non-energy optimization. So maybe about balance or uncertainty. Do you think that affects the motion that you can generate? Maybe for like a elderly patient, a person or something, they might not be totally optimizing for energy.
Yeah, it's a good point. And especially for gait, it's we always need to maintain balance. So yeah, it's correct. That's why maybe we use firstly the quadruped. No need to, but balance is easy to manage. So that's why only thinking energy, we could produce energy, and reaching also not well balanced. So no need to think balance. But you are right. Maybe when we go for biped robot case, maybe we need to also think about how to balance. Yeah.
Thank you.
Thank you for the great talk. I have a question about sensing. Can you comment a little bit about sensing? Because I think one of the things is the multimodality is also how babies learn, and we have very rich proprioception. And so do you think that synergy and all these nice properties that you want to emerge, they emerge thanks to, let's say, cross-modal learning, thanks to sensing? Or what's your comment on sensing?
Yeah, sensing, of course, it's the reinforcement learning. We use always that states. So, but it's true that we don't study well that which sensor is on and off, but this is very important point. Now, for this result, we use basically the access to all the joint angles, and we don't use torque information, but only for motion, joint angle information, it's possible to have this result. But it's important to, for example, having like force sensation or something, and for more interaction task, we need to use a sense of torque or force, I think.
Thank
you.
Any other questions? Meanwhile, we are handling technical issues.
Yeah, thank you for the nice talk. So how the inclusion of the synergy that was done mainly in the cost function then of your reinforcement learning? Or?
Actually, no. Actually, the point is we think basically that task performance and task performance per energy. So we optimize simply task performance and energy, and we checked if synergy emerge or not. So in fact, we never use the synergy explicitly. So this is the point. So we just try to find the reason why we have synergy. We use synergy. So we don't control synergy from
directly.
Outside.
And the quantification of synergy that you check then if it emerges, the level that is reached, is that comparable to the synergy that you see in real life?
You mean that comparatively to real? Yeah, I think we checked like rough motor performance change over energy efficiency. We check, but normally we check compared to literature-based information and how, for example, feed-forward, feedback switch during the learning and more qualitative way style, but we don't compare exact quantitative way yet.
Thank you.
Thank you.